Hello, I'm Shunji Kotsuki from Chiba University. I'm really honored to have this opportunity to present our research achievement or research progress on behalf of the project members. And first of all, I would like to thank all my project members for your hard work to make this presentation come true. So our project is aiming at the mitigation of the heavy rain-induced damage. And let's get started. So Japan has been suffering from the heavy rains induced by the water vapor coming from the oceans. And here I'm showing the two examples. So in these cases, we occasionally suffered from the catastrophic damages. And if we see the world, so we see the similar heavy rain due to the water vapor coming from the ocean. And so we have been thinking how to mitigate the heavy rains. And our idea is to generate heavy rain over the upstream ocean. So if we could succeed generating the heavy rain, then such heavy rain consumes the water vapor from the atmosphere. So that would weaken the downstream precipitation. So this is an idea of our project. But we also need to think about the scale of the phenomena. On left side, I'm showing the several atmospheric phenomena as a function of the horizontal scale or time scale. And in this Moonshot program, so Sawada-san and Furuya-san are working for the tropical cyclones, and Yamaguchi-san is working for the thunderstorms or urbanized deep convections. And in our project, so we are working for the stationary heavy rainfall, and we can roughly estimate the size of the energy. But we can notice that this energy is pretty huge compared to the human's capability. For example, so if we compare it with respect to the nuclear power plant or Japan's energy consumption, you can notice that so this energy size is pretty large compared to the human's capable interventions. So it means, so it's almost impossible to a dominant control is almost impossible. So therefore, so we need to introduce chaos control, to change the large atmosphere with limited interventions. So therefore, so there are two important aspects for weather control. So in our project, one of the key points is to intervene into the atmosphere or upstream ocean. So this is the first important point. And second one is a control theory is pretty important to controlling a chaotic system, to maximize the impact from the limited intervention. And so toward these directions, we organized our project. So actually, the weather control accompanies various problems, not only for meteorology. So we also need to incorporate mathematicians or engineer researchers to think about how to optimize interventions or how to realize interventions. And also, the weather control needs to involve the social scientists to think about the responsible research and innovation, to think about how to realize in society. And also, we need to design the society or law system, and we need to solve the legal problems. And toward weather control, currently our project includes 30 PIs and 150 participants as of now. And so, and we are working hard towards weather control. But so this fiscal year, so we determine the two actions. So one is to create synergy among researchers from different fields. So for the weather control, of course, meteorology or atmospheric science is pretty important. But we need to incorporate the researchers from other research fields. For that purpose, maybe we need to have a deep discussion. And the second action is from the feedback from the governing committee, in this March. So that committee's comments, one of the critical comment is feasibility of weather control is still unclear. And that comment notified us that so we or I have been working for weather control problem in computer or in our imagination. And but what I noticed or we noticed was the real weather control needs we need to act on the real world problems. And for that purpose, so we have started designing the seeding experiment this winter. And so this is the two actions we have been focusing on. And so let me explain about our research outcomes. So one is engineering research, how to realize interventions. And the first intervention is crowd seeding. And for that purpose, the 3 PIs are working hard with a company, Sugino Machine. And so the idea is we need to drop the dry ice from the aircraft. And our numerical simulation previously demonstrated that the altitude to form the ice nuclei is critically important. And because the aircraft can't go into the deep convection, so we need to drop the dry ice from the aircraft. So in this case, so we need to regulate the shape or size of the dry ice to reach the dry ice into the critical point. And for that purpose, we did the various experiments. And so in this experiment, so we dropped the dry ice from the 6th floor and measure the size or like terminal velocity. And what we found is that our measurement, black circle lines, are very different from the widely used equations. So, and in the real field experiment in this winter, we also plan to measure the such terminal velocity using the Doppler radar. And toward the real world seeding experiment, so we have been preparing. And the second engineering research is the dome. And for that purpose, so we are discussing with the Taiyo Kogyo company, so which has a very good skill to develop the large-scale structures. And the important point is that so we plan to use membrane. So here I have an example of membrane, and so this is like pretty light and pretty thin. So, but so the very small piece of membrane can withstand more than 400 kilograms. And so if you visited the Tokyo baseball dome, or if you visit the Tokyo station, so you can find such membrane-based structures. And so we are discussing so whether or not so we can generate artificial island based on this membrane-based structure. And so we are examining the feasibility of this dome. And with this company and our like a P project management group members, so we have been investigating whether it's feasible or not. And and what we are thinking currently is a truss-based structure, and that can be like put over the ocean, like with anchored by like ocean floor. And we also employ the FEM analysis, so how such truss-based structure changes with respect to the wind, and such as the max displacement and max test. And so our preliminary results are promising. So while the max stress at this moment is a bit higher than the maximum like membranes like a capability, but we are a bit optimistic. Maybe we can solve the issue by like a structural improvement. And so we are thinking to put it over the ocean, like to cause convection. And so maybe the potential for industrialization would be important. And if we could improve the skill of cloud seeding, that can be used for water resources or lightning mitigations. And another side, the artificial dome would be like applicable for like a greening in desert. So this figure is a kind of vision of the Taiyo Kogyo company. So maybe 20 years ago, so they developed design vision of their companies. So they would like to green the desert by like developing such large like artificial structure. And so maybe our like consideration can be a step towards the greening experiment. And if we could succeed it, maybe we can sell it for the other like countries, like they are in which they are suffering from the desert impact. Okay, so based on this engineering research, so we are also employing the various experiments using the weather prediction model. So first one is the seeding experiment. So we applied it for the Hiroshima's heavy rain in 2014. And in this case, so we got more than 200 millimeter precipitation over the 3 hours. And doing the Wolf model, so we implemented the function of the seeding. And so we saw that maybe the approximate 1,000 kilograms of the seeding can like change the precipitation pattern. And we also employ the like a damage reduction estimate using the landslide model. And in this particular example, so more than 200 million Japanese yen damage can be reduced due to the seeding, and it is much like higher than the cost for the seeding experiment. And the another experiment of the weather prediction model is like a dome experiment for the heavy rain case in 2015, known as the Kinugawa like a heavy rainfall. And in this case, we set these 33 domes over the upstream ocean, and with like a sensitivity matrix based optimization, so we found the optimal position. And in this case, so setting the domes increase the precipitation over upstream region and reduced precipitation in the downstream region. And in addition to this like a weather prediction model, so we employ the flood simulation based on the rainfall using the rainfall runoff inundation model widely used in this country. And so with this model, so we could see the changes in the flood. And without the dome or no control, we got the severe flood in upstream region of the Kanto region. But with dome, so we got the great reduction. And also, so we estimate the economical damage reduction using the model used in the insurance company in Japan. And we see the reduction in affected populations, affected households and houses. And so it means by coupling the hydrological model or economic damage reduction model, so we can estimate the impact to the society due to the weather control. Okay. So, but in addition to the weather control simulations, so we accompany the data simulation and to think about how to optimize intervention. And the question is, so previously we employ the single forecast, but the weather control should be conducted under forecast uncertainty. So here I'm showing the example of the ensemble forecast widely used for the weather forecast, and you can see the dissimilar precipitation pattern, and we are not sure which future can come true. And for real weather control, so such uncertainty in initial states of forecast should be considered. And for that purpose, so we coupled the model predict control with data simulation. So this is one of the big progress in this fiscal year. And what we developed was the so-called weather prediction model coupled with data assimilation and the model predict control. And by coupling the weather prediction model and data assimilation, so we can do the weather forecast. But in addition to the weather forecasting system, we couple the model predict control to optimize where to intervene into the atmosphere to change the future atmosphere. And so actually, Sawada-san also developed the same system, but we developed independently. But what we did is to employ this scale LTKF MPC experiment for realistic heavy rain case using the prep buffer observation. And we applied this for heavy rains in August 2021. And so we optimized the position of the dome. In this event, we got the heavy rain in Kyushu region. And so our optimal cost function of the experiment is to reduce the rainfall in the northern part of the Kyushu. And we optimize the place of the domes over the upstream ocean. And so before doing the control experiment, so we explore the predictability of the heavy rain. And so left side, so I'm showing the nature run. So that shows the heavy rain in northern part of the Kyushu. And the right side, so we showed the forecast from the OSSE experiment by coupling the by assimilating the prep buffer based observation. So it means, so we use just locations or height or type of the information from the prep buffer observation. And so we added the Gaussian noise into the nature and to generate the observation in controlled nature. And so in this event, so I'm just showing the deterministic forecast from analysis mean. But in this case, so we foresee the precipitation 3 days before. And so for this experiment, we employed MCC experiment. Okay, so this is the main result. And again, so we would like to reduce the precipitation in Kyushu region. And so on the left bottom part, so we are showing the place of the domes. And so we added an additional constraint so that the dome cannot move around. And so an additional constraint is that we assume that a line-shaped dome would be like effective. And so over the experimental period, the position or lines of the dome would change it gradually. But based on the ensemble forecast and model predictive control, so we optimize the place of the domes. And right side, so we are showing the two natures. So one is like true natural without control. So without the controls, so we got a series of precipitation in August 12th, August 14th, and August 16th. And that leads to the approximately 12 millimeter on average. But we employ the control simulation experiment proposed by Professor Miyoshi. And so green line shows the precipitation of the controlled nature. And the important thing is that we don't know this control nature. So we estimate the state of this control nature by adding the noise to the control nature. And we estimate this observation, like a prep buffer-like observation, to estimate the initial state. And based on this initial state, so with this uncertain initial state, so we employ the ensemble forecast, and based on this ensemble forecast, we optimize the place of the domes. And this reduced the precipitation. And if you could see the green lines, so we got like a great reduction in precipitation over August 12th and August 14th. And if we could see the accumulated precipitation shown by the dashed line, so we got the approximate 10% reduction of precipitation. But this result really encouraged us because it demonstrates that the intervention reduced precipitation under the state and the prediction uncertainty. And so, yeah, let me emphasize the achievement of this. This is very great work. And I think this is the first result that shows the feasibility of the heavy rain reduction using the realistic scenario with realistic observations. Okay, so let's see what happened in August 14th. So we got some differences between the nature run and controlled nature run. And so 3 panels show the precipitation at this time, like for nature run and controlled nature run, and their difference. And because our cost function currently is minimizing the precipitation in northern part of Kyushu, and because of that, so it's not perfect, but in general, we got the reduction in precipitation, like shown by the green color, blue color. And in contrast, so by adding the dome over upstream ocean, so that changes have the flow of the atmosphere, and we generally increase the precipitation over ocean. And what we are thinking is maybe adding the dome due to the increased precipitation over ocean, we got a reduction in precipitation in downstream region, and it matches our hypothesis. It means so if we could increase precipitation over upstream ocean, so we could reduce the precipitation in downstream region, and it's pretty promising, and also it also encouraged us greatly. And based on this experiment, we also consider how to operate weather control. And again, so one of the critical comments from the governing committee is a system of weather control. I mean, the operation of weather control is still unclear. And we have been discussing several researchers working for timelines or laws or disasters. And what we reached a conclusion that is, so it's good to propose the weather control operation based on the currently existing system, which is my timeline. So this my timeline is a widely used idea in disaster prevention operations in this country, so which define what they should do, according to the time. For example, for citizens or GMAs or local government or government office. So maybe they need to react on the changes in the weather situation, and so there are some definitions as a table, and so it means they already have such timeline. And in addition to this timeline, we can add the part of the control. And so what we additionally add is a control agency. And based on this control agency, so maybe suppose we could foresee the precipitation 5 days before. So we can start preparation. and maybe the accuracy or reliability of such heavy rain case can be becoming more and more reliable. And 4 days before, so we can move to the ocean, like to move the artificial dome or to prepare for the aircraft. And we are planning to do the weather control over 3 days. Then, so maybe by doing this, so we can, how to say, implement our weather control into the currently existing system. Okay, so, and additional thing, so what we found is that maybe it's good to focus on the tech force. So tech force is a kind of group under the governmental office, but so maybe once the disaster happens, so local government or governmental office should move based on the such warning information. But for very local government, such as under the prefecture level, then it's very difficult to react on the such situation. So therefore, so this tech force accompany the people for the local government, so that's to tell them how to announce to the citizens or how to prepare for the disasters. And it means, so this tech force is a very important office, to accumulate experience towards the disasters. So therefore, maybe so we are planning to set. It may be feasible to put this control agency under this tech force, and so this is what we are thinking currently. Okay, so and the final research is responsible research and innovation, and to discuss about how to realize in society. And for this research, we learned from the research for AI technology. So for the weather control research, so we need to address concerns from citizens. But there are various kinds of citizens. And such discussion have been done for AI research previously. So maybe there are many concerns such as privacy or accountability or safety and society and transparency or something. And so maybe if we just think about the concern, then it's very unclear. And we need to define what citizen concerns. And so therefore, so what we should have is what kind of concerns we should address for weather control. And so therefore, our research is doing to identify the discussion items. And for that purpose, so this November, so we plan to hold a seminar and workshop with citizens. And so as usual seminars, so I or some researchers will introduce about the technology of weather control. But the important thing is so we should obtain the feedback from citizens. So therefore, for that purpose, role-play-based workshop will be conducted. And so if you have some surrounding people who may be interested in this kind of workshop, so I would appreciate you could distribute this information for them. Okay, so and for future works, so we would like to realize the society safe from the extreme heavy rains by 2050. And as of now, so we are mainly doing the numerical experiment, but toward the Moonshot goal 8, so for the coming 5 years, so we need to start developing the dome. And also, we are planning to employ the seeding experiment. And for the LC and other issues, so currently we are trying to identify social issues. But for coming 5 years, so we need to estimate how much loss or how much cost is necessary for doing it. So this is long-term timeline. Okay, so I'm trying to summarize my presentation. And so this fiscal year, so we emphasized the collaboration between the different research fields. And actually such collaboration really accelerates our research and development. And this evening, we have a poster presentation. And so if you are interested, so please visit their posters. And the two take-home messages. And for controlling weather, so a control theory is pretty important. And as I show for the seeding experiment, so introducing a control theory is really promising to reduce the precipitation. And the second message is we are a bit optimistic that the weather control is achievable because we succeeded in weakening precipitation with prediction uncertainty. And that was enabled by the world's first enthalpy data assimilation MPC system for real event. And so tomorrow, Professor Yasunaga will present our seeding experiment. So this winter, we plan to act on the real atmosphere. So for that purpose, we started with dry ice seeding. And for enabling this dry ice experiment, so we have been doing various logistics, such as have the discussion with the aircraft company or to prepare the observations. And also, we made a series of briefings for local government and citizens. And actually, so maybe the acting on the real atmosphere is important for achieving the weather control. And so the Professor Yasunaga will present our plans for this seeding experiment this winter. Okay, that's all I have to say today. Thank you very much.
Okay, thank you very much. And now it's open to questions. Any questions and comments? Okay, maybe I have.
Shuchi.
Oh, okay. Shuchi?
Hi, this is excellent talk, and I see this is very nice overall planned. So my question is, for this type of heavy rainfall, so your focus is more like a stationary, more like, for example, like a frontal styled rainfall. So you need to consider the total accumulation time. So I guess my question will be, for this type of rainfall event, usually what we see is that it's really related to this long range, the moisture transport, and that's also related to very deep moisture depths. So when you designed all the experiment, how did you consider that? So I assume that for the, for example, for the flight or for the dome position, so how high you can go, and also, so is there any? I mean, when you design the experiment, is it possible to also consider the height? And also, for example, how early you can really. So I guess the idea that you want to do is go upstream and sort of like precipitate all those right. Most of the water vapor, right? So so how did you consider first the height, and also currently for the model, I think that we still have a lot of unknown about the hydrometer's behavior, the cloud physics. So you show a great potential for the model behaviors, but in the following, for your experiment, are you able to also incorporate the uncertainty of the different hydrometer? Because as I know, even for the WRF, if you choose a a different cloud microphysics scheme, then the things can get very different. So how did you consider all that? Thank you.
Yeah, so let me answer for your second question first. Maybe the addressing the uncertainty is important, as you mentioned, and the simplest answer is the usage of the multiple model. So, and the additional thing, what we are doing is that to develop an AI-based weather prediction system. And as you know, for the global scale weather prediction, currently the AI achieved the grid reduction for forecast uncertainty or forecast accuracy. And maybe we could use technology of AIs for weather prediction purpose or weather control purpose too. So because maybe having the AI can enabling us to use the auto-differentiable model or adjoint model, to optimize the intervention. And and that kind of AI can be also used for addressing the forecast uncertainty. Yeah, that is one idea what we are thinking. And for the first questions, are you thinking about the height of the dome or the seeding? Moisture.
Yeah, so for example, for the seeding experiment, how high you can go for the flight? Yeah.
Yeah, it's up to the aircraft, but for this winter experiment, maybe the currently we are thinking the 5,000 meter height. So because in this winter's case, the convective system itself is approximately 3,000 meters. So we plan to do it in winter first, because the dry ice seeding is effective for supercooled water-based convections. And in Japan, so there are some phenomena having such supercooled water in winter. So therefore, we will start with the winter experiment. And at this moment, what we are thinking is that we will do the summer experiment maybe 5 years or 6 years later. And in this case, we need to have the better aircraft to do the seeding from the much higher height. Yeah, but it's up to the aircraft, I think.
Maybe her first question related with the dome.
Yeah.
Height of the dome is only 500 meters. But she said that maybe the moisture is much deeper. So then how do you intervene the impact of the dome for reducing the rainfall?
Yeah, but our idea is to set the dome to initiate updraft. And fortunately or unfortunately, what we are targeting is stationary, a conditionally unstable atmosphere having the massive water in the lower troposphere. And so at this moment, we just see the slight reduction of precipitation at this moment. But if we could combine the various interventions to enhance such convections, maybe we could generate the deep convection. But so far, we haven't succeeded with numerical experiment. But we would like to initiate deep convection by combining the domes or shadings or other interventions.
Just triggering, right?
Yeah.
Yeah. Okay. Yes.
Yeah, similar to this question. The dome looks like placing the dome over there is placing artificial orographical blocking to induce orographic rainfall before it reaches there, right? Exactly. So in that sense, the slope or steepness of the dome maybe also you should consider that kind of thing. Yeah. What kind of slope of the dome may generate the storm earlier there, or how severe there, that kind of thing. So do you plan to have any design experiment for slope things? Yeah, we will do that. So in weather prediction model, currently we consider such like a dome as a drag coefficient. But as you mentioned, so there must be some optimal maybe as angles or height for like initiating the updraft. Yeah, and maybe we should do the CFD simulations together with the real experiment using the, how to say, to measure how the atmosphere changes. So we will do such simulations and experiment. Thank you very much.
Okay, any other questions? No question? Okay, thank you very much, Kotsuki-san.
Thank you very much.
Okay.